My name is Sam. I am a PhD candidate at the University of British Columbia, and today my talk is about resilient rivers and how glaciers control post-heatwave river flows across British Columbia. At the end of June in 2021, a globally unprecedented heat wave struck Western Canada and the Pacific Northwest. Temperatures skyrocketed up to 20 degrees hotter than normal, breaking all-time national records up to 49.6 degrees Celsius in Lytton. For context, this is 2 degrees hotter than ever recorded in Las Vegas, and the day after this temperature was reached, Lytton burned to the ground in a wildfire. Over 600 people died in British Columbia, and over 1 billion marine animals died on the West Coast shores. It was a visceral and profound event. I live in Vancouver, and experiencing this heat wave firsthand was really quite shocking, and it's shaped how I think about climate change. The heat was inescapable and widespread across the province. Because of this, all rivers in the province experienced exceptional temperatures. However, different rivers responded very differently to this event, in large part due to the role that glaciers play. Here are river flows for a river without any glaciers. In black is 2021, while blue shows the historical normal, and the shaded time period is the period of the heat wave. We observed that during the heat wave, flows increased due to snowmelt, but low flows occurred for months after the heat wave, in part due to the early meltout of snow. On the other hand, in this highly glaciated basin, there was a similar early rise in flow due to snowmelt, but through the remainder of summer, flows were within the normal range, in large part due to melting glacier ice. But this is a single example of a single heat wave, and we can think about this more broadly and ask, when, where, and by how much do glaciers control the streamflow response to heat waves? Today, we're going to dive into that question first by discussing some theory, then by simulating the role of glaciers during heat waves, and finally, we'll consider the broader picture and what lessons about resilience we can learn from these glaciers. Let's begin with some key concepts. Imagine a river with its headwaters in the mountains, as shown on the left. This mountain has a glacier and in winter is blanketed by snow. On the right, we have the river flow components. In dark blue is melt from snow, and in light blue is melt from glaciers. In winter, cold temperatures don't allow for melt to occur, so both of these flows are low. Then during spring, the snow rapidly melts and the river flow from snowmelt rapidly increases, but because the glacier is still largely blanketed by snow, glacier melt stays low. As summer goes on, the glacier ice is exposed and the glacier melts when it's then exposed to the warm air. During the late summer period, very little snowmelt occurs because most of the seasonal snowpack has melted away during spring. Now let's consider how this picture changes if a heat wave were to occur in spring. So in dashed lines on the right, we have the flows that would have happened without a heat wave, and we'll walk through how the heat wave changes things. During the heat event, snowmelt initially increases due to the warm temperatures. However, snowmelt through the rest of summer is reduced because the snow melted out earlier than it otherwise would have. A result of this early season snowmelt is that the glacier ice is also exposed to the atmosphere earlier in the season. Because the glacier ice is exposed earlier, it melts more than it otherwise would have, contributing more water to the river flows. So while snowmelt is reduced in the later spring and summer, glacier melt is enhanced, and so the glacier melt can compensate, creating a river that's more resilient in summertime to a heat wave that occurred in spring. On the other hand, let's consider a heat wave that occurs in summertime after that snowpack has already melted away. Glacier melt would increase during the heat wave due to the hotter temperatures, but snowmelt would not really change because there's little snow left to melt. So overall then, a summer heat wave causes an increase in water in the river due to an increase in glacier melt. The key takeaway from all of this is that the river response depends on both the qualities of the heat wave, like its timing and intensity, and also on the snow and glacier coverage throughout the basins. Now we can simulate river flows to understand and quantify the degree to which glaciers control river flows during and after a heat wave. To do this, we use a deep learning model that has been previously developed for river flow predictions in Western Canada. The model uses the past year of daily temperature and precipitation in order to predict stream flows at over 200 different locations. I won't get into the details, but the key takeaway is that the model is both accurate and interpretable. We can trust it to make the right predictions for the right reasons when it comes to snow and glacier melt, both during and after heat waves. To simulate a heat wave, we take two steps. First, we add in a 10-degree warm temperature anomaly for a 7-day period. Then we evaluate how the modeled river flows change. Here are some results shown for two rivers. On the left, a river without glaciers, and on the right, a river with many glaciers. The dashed black line shows the scenario without a heat wave, and the solid blue line shows a scenario with a heat wave in spring. Conceptually, we can see that the simulation tells us what we expected to find. Without glaciers, there is an initial increase in flow due to melting snow, but later in summer, flows are lower than they otherwise would be due to the earlier meltout of the snowpack. While for the river with glaciers, there is an initial increase in flow due to snowmelt, and summer flows are nearly normal due to glacier melt compensating for the earlier melt of snow. We can quantify the role of glaciers by taking the difference between the heat wave scenario flows and the normal scenario flows. Here, positive values indicate higher flows due to the heat wave, and negative values indicate lower flows due to the heat wave. We quantify the impact of the heat wave by two metrics. First, delta Q max, which indicates by how much flows increase during that initial heat wave. And second, by delta Q min, which indicates by how much summer flows have decreased due to the spring heat wave. The key here is that delta Q min should be closer to 0 for rivers with more glaciers, since that glacier melt is compensating. Now let's consider a summer heat wave. In the case without glaciers on the left, there is a very small response since the snowpack is largely already gone. However, for the river with glaciers on the right, there is a larger response due to the exposed glacier ice. Again, we can consider the difference between the heat wave scenario and the normal scenario, where positive values indicate when flows are increased due to the heat wave occurring. We can quantify the impact of the heat wave with, again, delta Q max, indicating by how much flows increase due to that heat wave. Conceptually, the key here is that glaciers make delta Q max more positive for summer heat waves. Keeping these two conceptual keys in mind, we can quantify delta Q min and delta Q max for spring heat waves in the top row and summer heat waves in the bottom row. We find results that make sense with our understanding of the problem. Rivers with more glaciers have delta Q min that's closer to 0 for spring heat waves, and delta Q max that's larger in magnitude for summer heat waves. What's important is that we've made this tool that can characterize and quantify these effects, and we can do it at a regional scale across British Columbia for many basins at the same time. Using this tool, we can better understand when, where, and by how much glaciers impact water availability during and after heat waves. Ultimately, these two metrics tell us two different stories. First, that glaciated rivers are resilient to spring heat waves, and that they transform summer extreme heat into cold, critically needed flows. To conclude, I want to reflect on the lessons of resilience that we can learn from glaciers as a society. To do this, I'll revisit the heat wave of June 2021. Even under such extraordinary circumstances, glaciers were able to create resilience in rivers across the province. For us as people, it's better, it's less volatile and more pleasant to live alongside resilience like this in the natural world. Our contribution with this tool today is an ability to quantify these glacier controls and the resilience they induce. However, we are rapidly losing our glaciers due to climate change, and a majority of glaciers in BC will disappear over the coming decades. While we've previously lived and grown in a place with a natural resilience to extreme events, this will no longer be true in the coming years. As a consequence, if we want to continue living in resilient places, it'll be up to us. It'll be our obligation to imagine and build these resilient communities. This talk has pulled together some thinking from across a few different projects that are listed here below. So if you have any questions or just want to chat more about any of this, you can email me or follow me on Twitter for further updates. Thank you very much, and I look forward to discussing this with you.